Let us discuss about electrophilic aromatic substitution today. Electrophilic substitution. That means substitution by an electrophile, an electron-loving species, which in this case, if you notice, is the chloronium ion. Aromatic means substitution of an atom in the aromatic ring. So, when we talk about electrophilic aromatic substitution, these type of reactions take place in aromatic compounds. One of the examples that we've taken today is replacement of the hydrogen of the benzene ring by chlorine atom to give us chlorobenzene. In the presence of anhydrous FeCl3, there can be other catalysts like anhydrous aluminium chloride, iodine, but these are all regenerated at the end of the reaction. Let us study the mechanism of this. In this mechanism, the first step involves the generation of the electrophile. As I said, it is chloronium ion in this case. So, ferric chloride releases chloronium ion, which will act as the electrophile in the second set. Now, benzene ring itself is very stable. Then, why should it attract the chloronium ion? The answer lies in the presence of the pi electron cloud, which is present above and below the benzene ring. We have the pi bond, pi bond, pi bond. So, pi bond, as we know, is perpendicular to the benzene ring, because of which there is a high concentration of electrons above and below the plane of the benzene ring. Hence, it attracts positively charged species, which in this particular example is the chloronium ion. It attracts the electrons from one of the pi bond, gets attached. Now, when electron movement has taken place here, there is a deficiency of electrons over here. With the result, this carbon in the benzene ring acquires a positive charge. We have done the concept of resonance. So, there are three different resonating structures possible in this case, and we have the final rhenium ion as the resonance hybrid. The last step. Now, this particular species, if you notice, the dotted circle is not complete because it's an unstable species. This has an excess of positive charge. This positive charge can be removed in the presence of a proton, which in this case is hydrogen, which is done in the presence of FeCl4 negative. If you notice, FeCl3 is regenerated at the end of the reaction, giving us chlorobenzene, HCl and FeCl3. There are other examples also of electrophilic aromatic substitution. You have the Friedel-Crafts alkylation, Friedel-Crafts acylation, sulfonation, nitration. All these are examples of electrophilic aromatic substitution. So if you understand one, you will be able to do the others yourself. One of the problems faced by the students is, or they get confused in writing these canonical structures. Please understand, first the movement of the electron takes place from the first carbon atom. It attracts, so we have a positive here, there will be no bond, and then alternate double bonds. Now again there's a movement of electron. With the result, this carbon now will be deficient in electrons. Acquires a positive charge, double bond, double bond. Last possibility is this positive carbon, either it can attract electrons from this end or the double bond on the right hand side. If I draw the electrons from this end, I will have again the first structure. The other possibility is drawing the electrons from the next set to the right. So with the result, this carbon acquires a positive charge. Or alternately, what you can do is 1, 3 and 5. These are the positions which acquire positive charge, in case you want to remember and not get confused. And then we put alternate double bonds. Hope this clears a little bit of doubt of electrophilic aromatic substitution. If you want to understand it clearly, it is better that you write these reactions yourself. Organic chemistry cannot be understood just by reading or listening alone. I always insist to my students that they should practice by writing in order to understand it fully. Any confusion, we also have a write-up of this on the same website. Hope you enjoy studying.